I will be talking about this isomorphism theorem for indivisible processes, and in this framework I will also demonstrate as one of the isomorphism theorems of Dynkin is coming from studies of indivisibility. So first I will need some kind of to establish language, and so my talk will be divided into 4 parts. First, introduction, then Levy measure on path spaces, path representations of Levy measures, and generalized Levy-Ito decomposition, and then isomorphism theorem for Poissonian processes. So Poissonian processes are not the Poisson process, but the infinite divisible processes without Gaussian component. So the general philosophy of this work is usually people begin with Brownian motion, then naturally is to extend to Levy processes and then Markov processes. The other way, start from Brownian motion, then the next step is Gaussian processes, and then you look at infinite divisible processes. So I'm just looking at the second part. So what is the notation? In this talk, T will denote an arbitrary non-empty set, so that would be an index set. T hat will be a family of all finite subsets of T. If we have a stochastic process and we have I included in T, a subset of index set, then X sub I is the restriction of the process X to the index set I. And in particular, if I is in T hat, then X sub I is a random vector in Ri. Definition is very obvious. The stochastic process is said to be an infinite divisible process if for every finite set I, a random vector X sub I has an infinite divisible distribution in Ri, which is really R to the power, the cardinality of I. So in other words, X is infinitely divisible if and only if for every I in T hat and N natural, the distribution of X sub I can be written as the convolution product of N copies of some measure mu sub I depends on I and N. So now the definition is simple. Now some examples. So we start with the first, the simplest example, the Levy process is infinitely divisible. Then fractional Levy process. So what we have, like fractional Brownian motion, we integrate the kernel T minus S positive part to power gamma minus negative S to power gamma positive part, and we integrate with respect to two-sided Levy process. The next one is Ornstein-Uhlenbeck process, and integration goes from negative infinity to T, and this is a solution to Langevin equation. So you have e to negative lambda T minus S dZs, where Z is a Levy process. Now, you cannot have this process if you don't assume certain condition about Levy process Z, and the condition is very weak. That is necessary and sufficient condition for defining such integral is just expectation of log class of Z at point 1 is finite. Now people are also, so Ornstein is very popular in mod modeling, and people are also looking not only into this kind of process, but also randomize lambda, so you have both lambda and ms chosen at random. So that would be another kind of infinite divisible process. The next one is a cylindrical Levy process. So U is a, say, separable Banach space, and the process L of t greater than 0 is called a cylindrical Levy process in this Banach space U if for every t greater or equal to 0, L of t is an operator, linear operator on U star with values in L0 on some projective space. So it's a linear and continuous operator, and then for every points A1 through AN in U star, the requirement is that if I evaluate this process and add the functionals A1 through AN, I will get an n-dimensional Levy process. So this kind of process were studied, being studied by David Applebaum and Marcus Riedl. Now, those processes can be also put in the framework of infinite divisible processes. Just we look at the two index consisting of time t and functional a, and the process given this way, operator Lt on a, and we see already that this index set becomes really big. So that will be one of the main problems of the general theory is that the situation when your index set is large. The next example of infinite divisible process is squared pestle process. So if we have a k integer, positive integer, then of course the squared pestle process is the norm of k-dimensional Brownian motion, and let's say squared, so you take power 2. More generally, if k is not integer, then for any real and non-negative lambda number k, the square of k-dimensional Pestle process is defined as a unique solution to such stochastic differential equation where W is a one-dimensional Brownian motion. So that's the example of Levy process, the infinite divisible process. The next example is squared fractional Brownian motion. So we have a fractional Brownian motion, and we take to the power 2, and the question is when this is infinite divisible process. And this question was, well, it has been in the case of h equal 1/2 Brownian motion has been answered some years ago. And Nati Eisenbaum in 2003 established this result that the squared fractional Brownian motion is infinite divisible process if and only if the Hertz parameter is less or equal to. The next example, squared Gaussian process. So we have a Gaussian process, and index now is by some space E, and so we assume that it's a mean zero Gaussian process, central Gaussian process, and say let's covariance function of this Gaussian process be g xt. Then we so E here is a locally compact separable metric space. And suppose that the covariance is actually a green function of a strongly symmetric transient Markov process. So the covariance is the potential, and so we are looking at this kind of Gaussian processes, which is called also the free Gaussian fields. And so then the squared Gaussian process is infinitely divisible, so we take the Gaussian squared. if and only well, if we assume that this is a strongly symmetric transient Markov process, then this quantum is in this divisible process. And it's the other way also. So that results in Eisenbaum and Casper. Okay, so we have enough examples, and they come from different areas. And now, so how to build some theory for such processes? So first we'll look at the d-dimensional case. So in d-dimensional case, any infinite divisible distribution is described by the generating triplet, sigma, which is a covariance matrix, and B, which is a vector in RD, and nu, which is Levy measure on RD, and this triplet is related to the Levy-Hinchman representation of infinite divisible measure. So I will not write this, but only to emphasize the conditional nu, that the conditional nu Levy measure is that it integrates x squared in the neighborhood of 0, and the measure is finite away from the neighborhood of 0, so which can be written by this condition. And in addition, nu of the origin is 0. This condition is needed for uniqueness. So now to look at those general infinite divisible processes, we say what will be the extension of this RD, so that when the process is defined on some parameter space T, then the natural where to put those measures would be R to T, the space of all paths from T to R. And we want to get a similar characterization in way of generating triplets. So first is that the such process, distribution of such process should be characterized by, well, the Gaussian, non-negative Gaussian covariance, and then non-negative definite function, sigma st on T cross T, and which we write sigma. Function B from T to R, and Levy measure RT on R to T and B to T, where B to T is the cylindrical sigma algebra, or the product sigma algebra of R to T. So to get this covariance matrix of the Gaussian part of infinite divisible process, that's very easy. The shift function is also easy. The problem is really to get Levy measure and to understand what this Levy measure is in this R to T, where T is uncountable. And so naturally we'll be looking at the finite dimensional distributions of infinite divisible process. Then when you take finite dimensional now corresponding Levy, the generating triplet, it will have some Levy measure nu, say sub I, if I is a finite subset, so you'll get the family of nu index by I. But then, by the properties of Levy measures, you will see that this is not a projective system of measures. So you have infinite measures which do not, are not projective systems. So you cannot really directly use any theorems in analysis on the existence of inversely unique projectivity of this system. So that, and the second, if you want to construct such a measure, this measure should be unique. And what is the corresponding in this R to T, what is the corresponding of this condition that nu at the origin is 0 when the origins are not measurable? Okay, so the definition of a Levy measure on RT-BT is that the measure mu is said to be Levy measure if and only if the condition of integrability here is satisfied, and now this the 0 at the origin is spelled out this way, that for every set in Pt, for every cylindrical set, nu of that set is equal to the inner measure of A with removed origin. So this makes sense and is just very natural condition, which will work in general. So first of all, when T is countable, then our condition is equivalent that nu at the origin is 0, which is this usual condition warranting uniqueness. So indeed, if we take this A equal the origin at T, and T is countable, origin is measurable, so you get on this right-hand side the inner measure of empty set, which is 0, so that will be the condition that nu at the origin is 0. And when T is uncountable, then this, of course, is not measurable, so that condition does not make sense, but condition given in the definition omits this difficulty. Now, you may look at this condition is how you can check that condition for every cylindrical set. So I have this lemma. So first condition is, so the condition on uniqueness, so that was this one, is equivalent to alternative of two conditions. One, either there exists a countable set T0 such that the nu at the functions which vanish at this countable set is 0, or another condition which looks very weird, that for every countable set T0, you can find another bigger countable set T1, T0 included in T1, such that the measure of the ring where you have X vanishes on T0 but does not vanish outside of T1, that measure must be infinite. So the alternative of those two conditions, which are of course disjoint, is equivalent to this condition for Levy measure.
Yeah. Should that be T1 complement? Should that be T1 complement?
I got yeah.
Sorry, the last should be T1 complement. X of T1 complement should be non-zero.
It is infinity.
It just means that at some point it's not zero.
The whole thing is not such zero.
Sorry.
Yeah.
And the second condition, I had the much worse conditions before, so then I helped, or just he found the condition to one condition which I'm not giving here because you will not be happy to see it, and this condition is more checkable. So there are ways to check the condition for Levy measures. And then you immediately have, once you have that, you can prove existence of this limiting measure, Levy measure mu, and it takes some steps, but eventually we have this Levy-Hinchman representation, and which is, and of course you have this. If you have such triplets, mu and sigma, the covariance function, and nu, which is Levy measure as defined, and be a function, then we have an infinite process. Now, for truncation function, I use the continuous truncation, so this is x1 divided by maximum x1 and 1, which is x1 between -1 and 1, and 1 divided by absolute value of x1. No way. Actually, sine of x1. Okay. Now, Levy measures for general process can be infinite, and it can be not sigma finite. So here is a condition when they are sigma finite. So Levy measure is sigma finite. Levy measure satisfy that condition which was one of the alternative conditions, this one. So there is a T0 such that this also is 0. And the third condition was about the Levy measure, the outer measure of the origin is 0. Now, so when the measure is not sigma finite, well, the not sigma finite measures which happen appear when you have very strange conditions like this. It's not clear how, if you can find the sigma finite, define sigma finiteness or characterize sigma finiteness of Levy measures in terms just of distribution of infinite divisible process. However, we have defined sufficient condition for sigma finiteness, to which we will come back later. And the stochastic process is said to be separable in probability if there is a countable set T0, such that for every T in T and epsilon greater than 0, if you take infimum over R in T0, probability that the distance of xt to xr is bigger than epsilon, that this infimum should be 0. So therefore, you can approach in probability every xt from x from T0, from T from T0. And so statement, this proposition is that if we have a separable probability divisible process with a separating set T0, then x has a Levy measure mu, which is sigma finite, and it satisfies some regularity condition which is parallel to the process. And more of these introductory things. So as I said before, that the process is called Poissonian if it's infinite divisible without Gaussian part. So in that case, the representation depends only on the Levy measure and the shift vector. Okay, so path representation of Levy measures. So in probability, we like to define measures of function spaces by looking at the stochastic processes. So naturally, Levy measures of infinite divisible process should be somehow described in similar way as measure on path spaces. So in terms of processes, but process depending on infinite measures possible. And so that's the definition. A family of measurable functions, ft in T on a measurable space as sigma algebra and measures n, is said to be a path representation of Levy measure mu if for every finite set I we have that the distribution of f restricted to I is, after removing the origin, is the same as the distribution of the projection of Levy measure on R to I after removing the origin. And the path representation is called exact if we have that the Levy measure is just n imaged by f, and also the sigma algebra generated by functions f sub t in the representation is equal to sigma algebra of this, the base space modulo measure f. So those exact representations, so how this is connected, for instance, with this the self similarity. If you want to describe the infinite divisible processes which are stationary or self-similar, you have to use a kind of representations, and but then you involve this operation of self similarity, and you want to get the same Levy measure, and therefore those are to get exact representation is important. Okay, so a path representation of mu is exact if and only if that's the way to check when is exact. So n composed with n negative 1 should satisfy this condition of Levy measure, and here the sigma algebras should be equal. And the second remark is that the exact representation always exists, and we just take this exact representation on canonical space, and the process is just the evaluation process. So once we have these Levy measures well defined, we are in here with shape with respect to representations. So now how to get representations? So we look at the infinite divisible process, and suppose it can be written as a stochastic integral with respect to some functions, collections of functions indexed by t and on S. And here I have the Poisson random measure and minus the centering. And I'm writing the centering different way that is usually written, because this is one integral. Usually people will take big jumps and small jumps separately, and then you have two integrals. This is the same, but it's to save the paper and show performance. And I get used to this. So, so it follows that if I can write infinite divisible process as the stochastic integral, then the kernel of this the stochastic integral is a path representation of Levy measure. So example now. So we take a Levy process, and so Levy process is given by a characteristic function, which is e to t, and then you have the Levy symbol C of u. And Levy symbol is given here. So now we take the Levy Ito decomposition of the process, and so we can write this process as the stochastic integral with respect to compensating that n is the Poisson measure of jumps, and minus uncompensated part plus the shift. And so this is to describe the Poisson random measure of jumps. Then we take a look at this formula, and we can write in the form like before that xt is just one integral, and you have a function f from 0 to t of r times x, and then is n dr dx minus dr rho dx, and divided by the whole thing here, and here is of course maximum, and this indicator is 0, 1, so it's easy to deal with. And so we can write xt in this form, from which we immediately see that the representation of Levy measure is that ft_rx. It is given on representation is on r plus cross r, and this is indicator of 0t of r times x, and so that this representation is also exact representation. So the Levy measure of Levy process is just the measure which is located on path, which just with jump one point jump path. So it's obtained this way that you run your t, and when it's t, then so it's just like that, up or down. And so the other way, so we can now summarize those dots and say that the stochastic process is if indivisible, if and only there is independent centered Gaussian process GT and a Poisson random measure n on a measurable space and a family of measurable functions ft, which satisfy this integrability condition needed for the existence of the Poisson integral and compensated, and such that for every t we have this representation which looks like this Levi-Ito representation, except this hidden distribution. So we want, of course, to get almost surely. So first of all, there's a lot of choices of this representation, and so the choice of particular representation in case of Levi process was because the structure of Levi process. And in general, there is for those generalized Levi-Ito decomposition, there is no uniqueness, but here's the theorem. So suppose we have an indivisible process which is separable in probability, then we can choose the Gaussian process n, g, and the Poisson random measure n, and exact representation f, which is defined on the Polish space, such that xt is given in this form, and for every t is the equation almost sure. And now about uniqueness of such a representation. So suppose you have two representations of x of this form, f1 and f2, on two Polish spaces s1, x2, and sigma finite measures n1 and n2, respectively. So then there is a measure preserving bijection from S2 to S1, such that the representation F2 is the equal representation of F1 composed with psi. So in other words, it's basically first to say there's completely non-uniqueness, but on the other hand, each representation is just change of variable from another representation. So there's uniqueness if you just divide this by with respect to those measure preserving transformations. Okay, so now we are moving to isomorphism theorem for Poissonian processes. So suppose we have a Poissonian process. So again, this meaning there is a process without Gaussian one. And suppose the distribution of this process is mu sub x. And suppose that it has Levi measure, it's as sigma finite Levi measure, mu on R. Take another process, which is just arbitrary process, it does not need to be indivisible, and which is independent of x. And with distribution mu sub y, which is not related to mu sub x, but related to Levi measure of mu sub x. So distribution of mu sub I, mu sub y, well, this distribution of y is, as distribution of the process, is dominated by Levi measure. Then there exists a non-negative random variable c with expectation 1, such that for any measurable mapping from the path space Rt to R, we have the expectation of this functional on the path space of xt plus yt, where t goes over parameters of t. This is the same as expectation of f xt, t belongs to t times c. And so therefore, if we take a Poissonian process and we add to this Poissonian process some independent process, but in such a way that this distribution of this process is dominated by Levi measure, then up to the change of measure, we are having still the same process. There's no effect. Okay. So this says, in other words, that if we take the distribution mu sub y, which is absolutely continuous with respect to nu, and this implies that mu sub y convoluted with mu sub x convoluted with mu sub y is absolutely continuous with respect to mu sub x. And if we also check that such a condition, then actually those two distributions, the convolution and the without convolution, are equivalent. Okay, so if you see shortly that if you were looking at the time at Dinkin's isomorphism, this is very much as these are isomorphism. And another theorem, which is from which I'm doing the previous one, and is also better for some applications. So suppose I have a process xt, and which is this Poissonian. So I already know that I can write this in stochastic integral form by this general level Ito representation. And then suppose I have a function q from the space S, which is a measurable space, into R plus, such that the integral of q dn is equal to 1. So put now C as an integral with respect to this Levy measure, the Poisson measure of q. And then we have for every measurable map f from R to t into R plus the expectation, and we have integral f with a shift, and here's a weight q dn is equal to expectation of f, and so this is a path, so I'm just denoting that this depends on the possible countable many t's, and is equal to this expectation of x evaluated also with many t's. So we know that in the Poissonian words, the admissible shifts, there is really not much to say. Usually there's a very trivial sets of admissible shifts. And here you can look at this theorem as there are a lot of admissible shifts. Actually, but you have to randomize it. So that's one way. So applications to application with path properties. All results which I'm saying here can be written to the Banach space variant processes. And in the next example will be, I will concentrate on Gaussian processes for the sake of presentation, but those computations goes for permanent processing in general. Okay, so here's this example of using this the previous theorem to obtain Dinkin's isomorphism theorem. So let's take a strongly symmetric transit Markov process in the space P and the Green function G. And since G is positive definite, there's a centered Gaussian process G with a covariance G x y is covariance x G, and which is with infinite divisible squares. So denote this process of squares of this Gaussian process by G squared. Now to get to the isomorphism, we take a family of local times of that Markov process V, and which are normalized to satisfy the condition expectation when you start for x, local time at y, level y, limiting infinity is g x y transient, so it stops increasing at some point. and fix point A from the parameter space E with GAA positive, and let PA tilde will be appropriate change measure for the Markov process B. So that means the Markov process starts with A, and the change is this H transform that under P tilde A, the process B starts at A and skewed at the last exit time from A. Eisenbaum and Kaspi showed that the law mu1 of the local time on the law is on R plus 2E is absolutely continuous with respect to Levy measure mu of 1/2 of G squared. So G squared is infinite as a process, but for the sake of computations, we are also always like 1/2. So for the computations, we compute the Radon-Nikodym is not difficult. Radon-Nikodym derivative of mu1, the law of local time, with respect to Levy measure of the square of Gaussian process. And what we obtained for the so this is Radon-Nikodym derivative here, and here is the variable. And then we evaluate random variable C for change of variable, and so using the previous theorem, and what we get very easily is that the change of variable formula is the Gaussian square process at point A divided by GAA. So now we take, as in the first theorem, we take the local time independent from the Gaussian process. And then using that theorem, we have that the expectation with respect to the product measure. So E tilde is the measure under which controls Lx infinity, and E controls the Gaussian process. This expectation is equal to expectation of 1/2 of Gaussian process squared, and with the change measure by Gaussian process squared divided by GAA. In other words, instead of expectations, you can use just distribution. So this is just saying the distribution of the independent local time and 1/2 of the square of Gaussian process is the same as the measured change distribution of 1/2 squared Gaussian process. And that what is called the Dinky's isomorphism theorem. And usually it takes a lot of development, and you can look at the book for Marcus and Rosen, for instance, which have this theorem and goes for a very, very long way. And just using even divisibility, we can get it quite simple. At least I can present it. Now, so then I said, okay, so what can we do as this isomorphism theorem like for the simplest case of Levy process? And Levy process, so we take the Poissonian process, and then so here we have this Levy symbol C, and in this form, here is the truncation. Well, we know what is the representation of Levy measure. This is the set of those functions which are constant, 0, and then jump, 1 point jump. So we are matching now theorem 2 on this isomorphism theorem. So here we'll know how to write it, and now only we want to choose a Q, and then we have the Z change of measure. Okay. So what would be natural Q So what the Q is just a function on from R to infinity, and it's just any non-negative function which normalized to the dimension. Then N is the usual the measure of jumps of process X, and so by Levita decomposition, so of course I'm repeating that, we have that is a representation of that Levy measure. Levy measure of the process Purkatasti on the path space. So then computation of this change of measure C format, so you integrate Q of V, depends on V, and does not depend on R, so you get the Q at computed at the jumps of X, and let's denote this by capital Q of X. And we obtain the following format that for any measurable map from R to R plus into R plus, the expectation, and you have the function Levy process plus this function 1 jump of Levy process, and then you integrate it to R and this function Q, which was chosen almost arbitrarily, and wrong. And that is the same as the expectation of the Levy process the sample in many points, and here is a change of measure format. So that's what we have for Levy process.
Okay. Now you just use t between 0 and 1 and not 1.
Oh yeah.
And actually at some point you drop the 0, 1 the integral. Yeah, I was worried with this silly question. Okay,
I corrected this wrong way.
No problem, no problem.
Yeah, no, thanks. So yeah, it was that we obtained only this statement. It should be 0.
No problem.
So therefore, such format, and honestly, I don't know. I have not seen that.
So here the assumption about Q is
No.
that there was integrability against.
Yes, only that integrates Levy measure. Okay, so the next one is the application of this isomorphic theorem for the path properties. And so quickly, if we have so this theorem says if we have a Poisson process with sigma finite Levy measure, assume that the path of X lie in the set U, which is Borel, for a sigma algebra of the product sigma algebra intersected with the trace on U, such that U is a subgroup of R to E under addition, then if we have a process with paths which are with distribution which is absolutely continuous with respect to this Levy measure, then the process pi must have also version in space U. The proof, as you see, goes very, very simply by this isomorphism, because we just look at this. So suppose that X has a nice path, and so therefore X will have will belong to some nice space U. With greater 1, and this path X also will belong to nice space U, and therefore, since it's a group property assumed about the path property space, then there's no for Y to be not. Okay.
for an answer in the flow to talk. Have time for questions.
So, if you come back to the slides on dignity isomorphism, the one you have in Marcus and Rosinski. So, what is the Levy measure, or what can you say on the Levy measure of the 1/2, the square of the Gaussian process?
So this is a loop measure.
Loop?
Constructed by Lejean, Marcos, and it's here the way going through this I2 Laplace is much faster and simpler, because here I can this argument I can write in half page.
Yes, and it seems because here you're using sort of count time, but in your theorem you just need domination. So it means that you can generalize the theorem. You can take other. What kind of generalization you can get?
Yes, but that's a very important point. Marcus and Rosinski wrote many papers and using this isomorphism theorem, and even when first I thought that this would be just Levy measure, and this only is absolutely continuous, and this distribution of local time, and so the isomorphism theorem would be much broader, much stronger if instead of x would be something like Levy measure, something which is distributed according to all Levy measure. But still, this is a cable with a lot of results. And another point is that in all development here, I was stressing that we know what the measures. That's a useful information process. Let me measure past uses.
Okay, Robert, you have a question? No, I thought you were going to.
Yeah, I have a question.
Oh, that's fine. Okay, that's fine.
I have a question.
You do have a question?
Well, so usually when there's a Levy process or field, you would like to have some sort of cat-like version. One version is nicer than another.
So, like, if you give, so sometimes, so important thing is also to have a good location for your Levy measure. So Levy measure should have be located, supported by also the Cadillac path. Here it goes only in one direction. And so the first step is to get a nice supported Levy measure. But sometimes it's impossible, and with the experimental processes, they are defined only by finite distributions, and you have no idea of the outcome. It's just some determinant and vice versa. So then approach is needed to assume that you don't, at the moment, first you don't know anything. And then having this model of stochastic integral representations, you can have series of inversion, also to reject on the dimension, you can move to output properties. So this is a general thing which you can start to do something.
Yeah. So I wanted to know if the run variable set, you always build it like that, as a density of. So how do you build a set, the run variable set? That is.
Which is the set?
C. Sorry, CE. The density that appears in the.
Yes. Okay. was here, and it's really this Q here is the okay. Here is the change of measure. You have N, which is the intensity measure of the Poisson random measure, and you change it to probability measure. So this Q is the and you take this here and you get the change of measure. And that in this argument, I use this representation just on this mass space, so that like people saw.
Okay, any other questions? Okay, actually, I have a question. Can we go to the last theorem, the very last theorem there? Okay, not this one. Okay, so the theorem basically says that the Levy measure is concentrated on U, right? That's what the theorem says.
Yes.
Okay, so it's okay.
Yeah. And yeah.
Okay.
So this actually we knew that, but this was by writing series of representations and so on. I was never happy with it.
Okay.
And it's good to get what you are okay.
Okay. If there are no questions, let's thank Jan once again.